Hey, welcome back to Coronavirus University, the online version of Math 235 at UMass Amherst this fall. It's been a bit. I wanted to come back to the dictionary that relates linear maps to properties of vectors, properties of maps to vectors. And this is an example I did in class for my students, but I thought it'd be good for review to just look at it a little more carefully. So remember that if we have a collection of vectors, say an ordered set of vectors, maybe I'll call these vectors in order, maybe A1, A2, A3, and A4. Okay, in general I might have n of those vectors, but let's take n to be 4 here. If I have a collection of these vectors, I can associate that ordered set of vectors with a linear map. The linear map is ends up in the same space as the vectors are, so the codomain is going to be R3, and the domain of the map is just, well, it just depends on the number of vectors I have. There are 4 vectors here, so it'll be R4. So I can think of a set of vectors, an ordered set, as giving me a linear map from R4 to R3 in this case. Okay, and how do we actually specify the map? Well, we say we're the first standard vector E1. So E1 would be the vector 1, 0, 0, 0. We specify where it maps to, and it's going to map to the first vector in the list, namely 1, 2, 3, which is A1. Okay, and similarly, the second vector, standard vector in R4, E2, it's going to map to where? Well, it'll map to A2, the second column, the second vector in the list, and so forth. E3 will go to A3, and E4 goes to A4. Okay, and that completely specifies the linear map. Okay, that uniquely specifies it. In fact, we can think of the linear map as given by T of x equals matrix multiplication by x. Okay, in other words, so x is a vector here in R4. This is where x lives in R4. In other words, this is what? This is x1 a1 plus x2 a2 plus x3 a3 plus x4 a4. X, of course, is the linear combination of E1 through E4, namely x1 down to x4, if I was write as a column. So that's the linear map. Expressed as matrix multiplication. And yet another way to say this is that I've got the matrix for T, this linear map, the standard matrix, is just the matrix A, whose columns are A1 up to A4. Okay? So this is saying that, what does this say then about these vectors here? Well, it says the span of this set A1, A2, A3, A4, okay, what does it correspond to? Well, this tells us that it corresponds to things that are in the image of T, right, or the image of A. So the span of this corresponds to the range, or the image, the range of T, or the image of T, of this linear map, okay? So the image of T, I sometimes abbreviate as just MT. That's the standard notation. Okay? All right. So that's the general thing we did. Now let's actually try to figure out what that image is, or equivalently, what the span of these vectors would be. Okay? So how do we find that? Well, we need to find out what vectors can be written as a linear combination of the columns, or what vectors, right? We can solve the equation ax equals b. That's what the image is. It's the vectors b of this form, vectors in R3. So it sits inside, the span sits inside R3. But how do we actually do that? Well, it's our old friend row reduction. Okay, so how do we find this? In fact, we can also understand the relations. So we're going to actually understand the relations among these vectors at the same time as we understand what the image is. So we can actually get at both of these what the span is, and also what the relations among these vectors are, using row obs. on the matrix for this. So what's the matrix A? Well, the matrix A is, of course, just the matrix's columns here. So let's do that. So on A, which is the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These columns were these vectors in order, or if you like, the standard matrix for the corresponding linear map. Now, I won't do all the row operations, but let's just indicate what they are, okay, and you can carry them out. So the first thing we want to do, of course, is we want to eliminate these two entries. And if we do that by subtracting twice this row and 3 times that row, we'll get a matrix actually that turns out to have the second and third rows proportional. And if you carry that out, you'll see that that forces the third row to be all zeros. This was a 0 by our construction. And what you'll end up getting, if you do this carefully, is you'll see that you get 1, 2, and 3 in the second row. This is after doing several row operations. And then you can back substitute, or in other words, subtract off this, a multiple of this from this. And when you do that, you'll see you get 1, 0. We're trying to make that into a 0. Watch the last video about row reducing a matrix of Baklava, a different way of doing row reduction. Anyway, and I think the remaining thing here, I think I wrote this down so I make sure I don't make a mistake with the signs. I think the remaining 2 entries are that. Okay, so this is the RREF of A, which is what tells us a lot about the image. What's the first thing it tells us about the image, about the range of T? Well, that row of zeros means that I can't always solve the equation AX equals B. In other words, this is not all of R3, okay? The image is not all of R3. It's actually what? It's actually a plane in R3. Okay? And what plane is it? Well, it's the plane spanned by, well, not these 2 vectors. These are the pivots. Again, remember, these are the pivots. The plane is actually spanned by the corresponding pivot columns here. So the plane you get is actually the span of the first 2 guys, A1 and A2. In other words, well, let me write as A1 and A2, just to save space. Okay? Okay. But we can say more. So what happened to the vectors A3 and A4? Well, the vectors A3 and A4 actually could be written as linear combinations of A1 and A2. Okay? In fact, we can read them off directly from this. From this, we read off, what do we read off from this? We can read off a linear relation. I'll write it a slightly different way, a linear relation. Namely, A3 is the same linear relation as to A1 and A2 as this guy is to the reduced pivot columns. Okay, so let me just indicate this, and I want you to check this. Notice what's this? This is -1 times the first column, 2 times the second column. It's the sum of those 2. Okay, so this implies, these numbers here tell us that A3, so this is one way to write the linear relation, is to express A3 as a linear combination of these 2 vectors, which we know it can be because the image is the span of these guys. It simply says this is -1 times A1 plus 2 times A2. Okay? And this fourth column tells us the linear relation expressing A4 as a linear combination of these guys. Okay? Namely, again, same idea. This column is -2 times the first column plus 3 times the second one. That tells us that actually this column, 10, 11, 12, A4, is a linear combination of these 2 vectors with the same coefficients. So this tells us that this is minus 2a1 plus 3a2, which you should check. Okay, you should check that yourself. So please check this. Check this. Okay, so there we have it. We've worked out the linear relations. We can actually write it different ways. We can actually get all linear relations. How do we get all linear relations? So these are two linear relations, but all linear relations would come from looking at the free variables. So these are the free variables here, right? Corresponding to these things I did. Notice that the relations come from the free variables, and you could write out what all the linear relations might be. And let me write that. What are all the linear relations? All the linear relations are the things that solve the homogeneous equation, right? So the linear relations, we look for all of these correspond to solutions x in R4 to ax equal to 0. And we can write down using these two variables as these two free variables as parameters. We can write down what those are, and we can just read it off now. What are the x's? Well, the x's that solve this are going to be something involving x3 and something involving x4. And I'll put the not yet known vectors in here. And how do we find those? Well, we can find these vectors. These are vectors in R4. We can find them by setting one of the free variables equal to 1 and the other free variable equal to 0. In this case, they're 2. So in general, if there are a whole bunch of free variables, we set them in turn, one free variable equal to 1 and all the rest equal to 0. And when we do that, let's just see what happens. If I set, and we can do that over here in the RRAF, of course. Okay, so if I set x3 equal to 1 and the other one equal to 0, so I'll put a 1 there and a 0 there. Okay, the first row is the equation that tells us what x1 is. Okay, so if x1, we're reading that first row, that says that x1 plus 0x2 plus minus x3 plus 0 equals 0. We're solving this equation. So that tells us that x1 is 1. Okay, and now I'm going to figure out what this guy is by reading the second row, which is the second equation. Namely, it says that x2 plus 2 equals 0. So this has to be a minus 2. Okay, so that's one of the vectors that one of the minus 1 minus 2 1 0 is one of the linear relations among these. In fact, if you look carefully, it's this linear relation. So this guy here, this linear relation right here, this vector right here, just re-expresses this linear relation right here. I want you to check that, okay? Okay. So the other guy, the other solution to the homogeneous equation, okay, we get by setting x4 equal to 1 and x3 equal to 0, okay? And that should correspond, as you might guess, to the second of these. Okay, so this one should correspond to this one. Okay, so maybe you can read it off already what these guys are, but let's just fill them in using the method we've been doing. Namely, since x3 is 0, the first equation, the first row says that x1 plus minus 2 is equal to 0, so this should be a 2. Okay, and the second row tells us that x2 plus 3 is equal to 0, so this should be a minus 3. And that's the relation I wrote down right there. This says that this relation here says that A4 is minus 2A plus 3A2. Or if you make it homogeneous, it says that 2A1 minus 3A2 plus A4 equals 0. Okay, so that's another thing. So we get all the relations, all possible linear relations come from looking for the solutions to the homogeneous equation, the fact that I can write A3 and A4 as linear combinations of A1 and A2 says this set is not an independent set, it's a dependent set. We've actually explicitly written out what the linear relations are. We wrote out what A3 and A4, how they can be expressed in terms of A1 and A2. But this also gives you a picture of all the other possible relations among the four vectors. Okay, so that's the summary of this. I think you should study this example more because I think it illustrates, I said, the interplay between the role of a set of vectors in order and a linear map and the procedure for finding the image. And as I said in the general lecture, the set of all linear relations, which is equivalent to the x's that solve ax equals 0, actually is another important set that occurs in linear algebra. It's a subset of the domain of the map, and it has the name the kernel. So this leads to something we'll do in the next chapters. Well, chapter 4. This leads to the notion of the kernel or the null space of T, and the fact that it's a non-zero subspace tells us that these vectors are linearly dependent. If it happened to be 0, if there's only the trivial linear relation, then the vectors would be independent. Okay, so that's the story.